Welcome back to our fourth video of writing an MNIST classifier from scratch. In this video, we're going to define a function for checking the accuracy of the model. Previously, we imported the packages, we wrote the model class, we defined the hyperparameters, device, model, optimizer, loss function. We downloaded the MNIST data, we wrapped data loaders around the train dataset as well as the test dataset. Then we defined the training loop. I showed you how it is important to have 4 items defined for our training loop. Now in this case, we're going to be needing to write the check accuracy function because we were not able to check the accuracy of our model previously. And checking the accuracy most likely is going to be done by some data set that the model hasn't seen during the training. This is just to make sure that the model is generalized. We want the test data to be unseen by the model. Hence, we're going to use the test loader. So, in order to do that, I'm going to start by defining a function, accuracy calculation. And if you think about it, we just need two inputs for this function. One is the data loader, and next is the model. Initially, I'm going to define 2 important parameters. Number of corrects, which reflects the number of correct predictions throughout the entire test loop, and also number of samples, which is going to reflect the total number of samples. And we also need to put the model on eval mode. This guarantees that the model is not going to get entangled with calculations of gradients during the test loop, because in testing we're not doing any training. We don't want the gradients to get calculated, which would be only used in the backward propagation. We're not doing that, so we don't want any processing resources gets involved with calculation of gradients, which is, by the way, a highly expensive process in terms of processing. So now I'm going to write the test loop. Before writing the test loop, we would like to use a with statement to declare to Torch that we don't need any gradient to be calculated. Again, we would like to make sure no processing resources is going to be wasted on calculations of gradients which are of no use during the test. Now I'm going to write down the test loop. This is very similar to the training loop. Again, we're going to say for x and y in loader, and remember that we had 4 items in the training loop that we needed to touch base. There are 4 items here, 3 of which are exactly the same as what we had in the training loop. So let's just comment them out as in order to have their place reserved. First one is send the data to the device. Next one is prepare the data for the model. Next one is forward propagation, which is propelling the data into the model. And last one in the training loop was the backward propagation. As I mentioned, we're not doing backward propagation because the only purpose behind the backward propagation is the training. We're not doing training here. What we need to do is to do calculations for accuracy. Sending the data to the device is the simple part. X is equal to x dot to device. Y is equal to y dot to device. Preparing the data for the model is also simple because we have to reshape our input 784. For the forward, it is also very simple because we're going to say y hat is model x. And now we need to calculate accuracy. For calculations of accuracy, the one thing we need to do is to find out that out of those 10 numbers that are predicted for every single image, which one is the maximum? And the value of that is not important, but the index of that is important because that index is going to indicate which class that image is predicted to belong to. So hence, I'm going to say underscore and predictions are equal to y hat dot max of 1. And this one makes sure that not only we calculate the maximum under underscore, and also the index goes to the predictions. Next, we're going to say num corrects is going to be summed with. It's going to be summed with those predictions that are equal to their label, and from whatever number they are, we're going to sum them up. So if there's 4 correct, the value is going to be 4. And num samples is going to be summed up by predictions dot size 0. So at this point, we are pretty much done. The only thing I need to do is to, at the end of this for loop, have an fs string printed that will report the accuracy. So I'm going to say accuracy is equal to num corrects divided by num, divided by num samples times 100. We would like to percent of accuracy. And we would like this number to have 2 number of decimals. We can also print the number of corrects over total number of samples. And keep in mind, when it's done, we gotta return the model to the train mode. And the main reason is that at the end of each epoch, we're gonna call the accuracy, we're gonna calculate the accuracy on the eval mode, and we're gonna put it on the train mode again so that for the next epoch, the model is set to the train mode. I'm gonna run this, it's fine. Then I'm gonna go down here, and what I'm gonna do in the training loop, after printing of the number of epoch and the loss number, I would like to have accuracy calculation function with the test loader and the model to kick in. And that's all. Let's just see what are the results. We should get first the epoch number and the loss value, and then quickly we got to get an accuracy and the number of corrects over the number of total images in the test dataset, which is 10,000. And now you can see that not only loss decreases, but also accuracy increases. We have an accuracy increase from 89.86% to 91.57%, and then to 92.49, and this goes on, and we can get a better results. So at this point we're done pretty much by with writing our MNIST classifier from scratch. We did a lot of work here. We basically learned how to write a model class. This is very important. And we also learned how to write a function for checking the accuracy in the test mode. And we learned how to import, download the MNIST dataset. It could be any dataset, and also make data loaders for that. We also learned how to write the training loop, checking the accuracy and everything. We had, with a very simple model, we had 93.72% accuracy. I think the best accuracy that so far has gotten on the MNIST dataset is 99.92 or 91%. It is a specific type of convolutional neural networks that does that. Keep in mind, not only we don't have a convolutional neural network here, the fully connected layer network that we have is a very simple fully connected layer network with no hidden layers. I'm gonna release a new video in the near future under this series where not only we're gonna optimize and fine-tune the hyperparameters that we have here, but also I try to make this fully connected layer more complicated by adding hidden layers and changing the number of parameters so that we could see how we can improve the accuracy of this model. But until then, please practice as much as you can with the items that I provided you here with. Remember, the empty notebook as well as the completed version of this notebook can be found in the GitHub link that is under the video. So please try to go there. If you have any question, comment under the videos and I will try to respond as soon as possible. We would like to have a community here in order to open the discussions and talk about the fundamentals of writing classifiers and deep learning models in Pytorch. Thank you so much.